Hello, Riles. This is part 3 of our course review, looking at question 8, 9, and 10 of our review sheet, exponential and trigonometric derivatives. So we're on question 8. We are given a couple of trig and, question 8 focuses on trigonometric expressions, and we are asked to find an expression for delta y by delta x in each one of these cases. We tried to avoid some of this ambiguity in our coursework, but we should know how to interpret this. This is not the square of the sine of x. That would be written as with an exponent here or with brackets. It is considered a little bit ambiguous about what is being squared, and it would really be helpful if there were brackets around the argument for the sign ratio, but it should be interpreted in this way. And that's important because if I look at question B, I need to know what is on the inside and what is on the outside. I need to know the order of my operations. So let's figure this one out. The derivative of the sine of something is the cosine of something. I have to multiply by the chain of the derivative of that thing. I'm going to leave these, I think, mostly in this order. If the directions were do not simplify, this is what I was going for on a couple of our tests. And I was actually a little concerned when students were simplifying because it didn't show me them working through the chains in the proper order. You don't have to put this 2x out front. I mean, most solution manuals will have it there, but let's leave it like this so that our reader sees we did the derivative of the outside with respect to the inside times the derivative of the inside with respect to x. A large set of brackets there might be good. For option number 2, let's look at the function. I'm going to rewrite the sine of x squared as the sine of x squared. I should never read it as sine squared of x because I can't square sine. A couple of students tried writing ln squared or log squared, and that's just not a thing. I think this is a awkward notation that should be avoided. That shows me what's my inside and what's my outside. The derivative of the square of something is 2 times that thing. To the exponent 1 multiplied by the derivative of that thing with respect to x. Now, I could write that as the sine of 2x, but why would I really? I mean, there's absolutely no advantage to doing that. Question C, we have a relationship that is defined implicitly. We have y is the sine of x times y. Let's take the derivative with respect to x of both sides. I'll get dy by dx on the left-hand side. And then I'm taking the derivative of the sine of something, that is the cosine of something, multiplied by the derivative of that thing with respect to x. I'm going to switch to a product rule. Derivative of the first times the second plus the first times the derivative of the second. Good. And we were asked to find an expression for dy by dx, so I feel like I should isolate dy by dx. Let's distribute on the right-hand side. I'll have y cos x y plus x. I was thinking about in what order I wanted to write this. Then I realized it doesn't really matter. I'm going to subtract, I think I'm going to subtract x dy by dx cos of x y from both sides. So I'll have 1 dy by dx minus x dy by dx cos of xy equaling y multiplied by the cosine of xy. I'll remove a common factor, dy by dx. Common factor 1 minus x cos xy equals y multiplied by the cosine of xy. Where does my common factor end? Right there. And then I'll divide both sides by that expression. So I'll get dy by dx equals y multiplied by the cosine of xy all over 1 minus x multiplied by the cosine of xy. Sorry. Come. Let's see. D, I'm wondering if maybe I should simplify the expressions first or see if I can use some identity skills to maybe get rid of this quotient here. I think I will. The first thing I'm going to do is I'm going to use the distributive property. So I'll write that as the reciprocal of the secant of x plus the tangent of x divided by the secant of x. Next, I think I'll reciprocate a secant ratio to find a cosine ratio. Here, let's maybe just take our time here and write this as the sine of x divided by the cosine of x divided by the reciprocal of the cosine of x. Then I can multiply by 1 in the form of the cosine of x divided by the cosine of x and get cosine of x plus the sine of x. Like with a number of our exponential relations, doing a little bit of work with the function before differentiating, I think, really pays off. Because I'm going to find this a lot easier to do. dy by dx is derivative of the cosine of x, that's the opposite of the sine of x, plus the derivative of the sine of x, that's the cosine of x. I mean, if I jumped right into the quotient rule, I'm just going to have a lot more work to simplify it down to this expression here. We'd be talking about the derivative of the top, derivative of the tangent of x. Tangent of x has cosine of x in the denominator, so does secant of x. So it'd be secant of x squared multiplied by the secant of x. That's the derivative of the top times the bottom, minus the derivative of the bottom, c plus theta, secant of x times the tangent of x, multiplied by the top, 1 plus the tangent of x, all over the bottom squared, secant of x squared. So yeah, I've got my work cut out for me to simplify this expression, or even to find dy by dx when x equals, I don't know, like 60 degrees or something like that. This expression is much easier. I would choose simplification all the time. And E is y equals the square root of the secant of the triple of x. Maybe I'll just rewrite that as the secant of 3x to the exponent 1/2. I don't want to, I know I can build the expression for the derivative of the secant of x. I think you heard me doing that earlier, so I don't see the need to rewrite this as a quotient, and I definitely don't want to use the quotient rule when I have a constant numerator. Let's do dy by dx is the derivative of the square root of something is 1/2 times that thing to the exponent negative 1/2. And I multiply by the derivative of that thing. The derivative of the secant of x with respect to 3x is, well, the secant of x, its derivative is going to have two factors. One of them is going to be the secant of, sorry, maybe I should say the secant of u is going to be the secant of u. The other factor is the factor that also has a factor of the cosine of u in the denominator, which is the tangent of u. Maybe you heard me saying theta earlier. It is not a cofunction identity, so it has a positive leading coefficient. So I did the derivative of the square root of a radicand with respect to the radicand is 1/2 times the radicand to the exponent negative 1/2, multiplied by the derivative of the radicand. The radicand is the secant of 3x. The derivative of the secant of 3x with respect to 3x is, or the secant of an angle with respect to an angle is the secant of an angle times the tangent of an angle. And now I complete my chain by multiplying by the derivative of the angle with respect to x. And you can simplify that one if you want. There's a couple of things that'll happen there, but I'm more interested in the derivative rules. Okay. For exponentials, maybe we should review our exponential rules. The derivative with respect to x of e to the x is e to the x. The derivative with respect to x of b to the x is going to be a multiple of b to the x as well. We just need to multiply by the natural logarithm of b. You don't need to multiply this by ln e. This is the original rule. This is an adjustment of that rule if your base isn't the natural base. This is why I was concerned when students were using this rule to differentiate a natural base, because we used this fact to prove this rule. You were putting the cart before the horse, they say. You were mixing up the order of things. The derivative with respect to x of the natural logarithm of x, is the reciprocal of x. Same argument here. Please don't use this general rule to differentiate the natural logarithm of x, because we use this fact to prove this. The derivative of the general logarithm on x is going to be the reciprocal of x multiplied by the reciprocal of the natural logarithm of your base. Okay, you can just use the change of base rule there as well, I suppose. So for question 9, we have f of x equals 2 times e to the x divided by 1 plus e to the x. I might treat this as a constant multiple, just so that my derivative is a little bit easier. I will communicate that I am differentiating right here. This is interpreted as the derivative with respect to x. That's clear in Leibniz notation. It is not clear when you write y and then just y prime. So constant multiple followed by a quotient rule. Derivative of the top times the bottom minus the top times the derivative of the bottom. Derivative of 1 is 0. Derivative of e to the x is e to the x. All over the bottom squared. 1 plus e to the x squared. Okay, now I could remove a common factor or expand and simplify. Plenty of algebra available there. Let's try g. G, I see, I'm taking the natural logarithm of a quotient. So I could use the chain rule here and take the derivative of the natural logarithm of something and then follow that up with a quotient rule. But how about instead of using the chain rule and the quotient rule, I use a logarithmic property. This is a logarithm of a quotient, and I know that if I'm dividing two powers on the same base, I can keep my base and subtract my exponents. This gives the most efficient solution instead of just trying to memorize derivative rules and jumping in. Now I can say that my derivative is going to be the reciprocal of my power multiplied by the derivative of my power minus the reciprocal of my power multiplied by the derivative of my power. And I could get that as a common denominator if I want, but I don't want to. So I move on. C, I think we've seen something like this before when we were asked to find multiple derivatives. And I'll have the same argument here as with the trig. I'd really like to see your work when you're showing your work. I'd like to see the work in the order in which it should occur. So I'm not taking the derivative of 2x first here. A lot of software will spit that coefficient out first, but we shouldn't be using software to differentiate this. H prime of x is going to be, well, this is an exponential function, so its derivative is also going to be exponential. It's not a natural base, though, so I need to multiply by an adjustment of the natural logarithm of that base. And now I complete my chain by multiplying by the derivative of that exponent. There's absolutely nothing wrong leaving that as 7 to the exponent 2x times the natural logarithm of 7 times 2. There's no need to write that as, say, a base of 49. I think that makes your base larger and makes it a little bit more complicated. And I just don't see putting the 2 ln 7 out front here. If my reader sees 2 ln 7, they're going to say, wait, question number 1, where did the 2 come from? You say, oh, it's the derivative of the exponent. Well, I haven't done the derivative of the exponent yet. That was the last thing that I should have done in my chain. So show it last. Let's see if we can find some log properties in D. We've got L of x equals log base 2 times the square root of x squared plus 3x. Now don't go searching too hard. I mean, like I could write this in factored form, and then I would have a product, and I could use the property of the log of a product and add those two logarithms together. But I'm really exchanging, like I'm not seeing a product rule right now, so why am I trying to avoid dealing with products? One suggestion that a lot of students really took to was instead of having to memorize a different derivative rule for general bases for logarithmic expressions, is you just always use the change of base approach before you differentiate. Because if you use your change of base approach, then you're going to have a constant multiple. Let's keep going with this function before we even differentiate. Maybe I should have taken a line to do this as well. The square root of x squared plus 3x is x squared plus 3x to the exponent 1/2. Actually, I'm going to write that on my next line. I think I'm going to write that as a constant multiple of the reciprocal of the natural logarithm of 2. So this is the power of a power, and when evaluating the power of a power, I can keep my base and multiply my exponents. So another constant multiple times the natural logarithm of x squared plus 3x. So I probably should have tidied this up a little bit faster. I'm just going to treat this as, you know what? I'm going to write it as a quotient because I want to cover, again, the fact that we should not use the quotient rule when your denominator or numerator is constant. I'm going to differentiate from that format right there. Here we go. L prime of x is going to be the derivative of the natural logarithm of a power is going to be the reciprocal of the power multiplied by the derivative of the power, 2x plus 3. And now I kind of regret not having that as a constant multiple. How about we just put that over here to ln 2? Put that in brackets. So constant multiple, derivative of the natural logarithm of a power is the reciprocal of a power multiplied by the derivative of the power with respect to x. So I realize it took me a number of steps to get to this point, but isn't it nice that I just differentiate in one step with fewer chains? I think so. The logarithmic differentiation was another task where students weren't showing the steps at an acceptable level on a number of assessments. You really need to convince your reader where the expression for the derivative is coming from. You have a variable base and a variable exponent. That's problematic. To deal with that, we take the natural logarithm of both sides. So we show our reader that we're taking the natural logarithm of both sides. Then we show our reader the property that we're using. Again, that the power, to simplify a power of a power, I keep my base and I multiply my exponents. And now I can show my reader that I am differentiating on both sides with respect to x. So there were 3 or 4 steps in some cases that weren't shown. And it is the steps that will demonstrate your understanding, not the answer. A couple of chains here. The derivative of the natural logarithm of y is the reciprocal of y multiplied by the derivative of y with respect to x. The derivative of this expression, I'll use a product rule. The derivative of the first multiplied by the second plus the first multiplied by the derivative of the second. And I'll show that for my reader as well. I think a couple of ones just showed up here. Well, show your reader where one comes from. Okay, your reader will not be convinced that you understand what is going on. Let's multiply both sides by y. I'll get natural logarithm of x plus 1. And usually, and in this case, for example, we are asked for an isolated expression for delta y by delta x in terms of x. So we just replace y. Now, on this step, right now, we replace y with x to the exponent x. And that explains to our reader where x to the exponent x comes from. Okay, but like a jump from here to here is absolutely unacceptable. It wasn't a multiple choice question. Sorry, I'm speaking about a small minority. A large number of students showed these steps, and I'm sure you will continue to do so. Okay, let me know if you have any other course review questions, and good luck with your other courses.